So the first, I've thought about whether to actually announce this or not, and I go back and forth. So I'm going to send a written announcement out as well. So I know a lot of you guys are stressed about the assignments, um, quite rightly so. It gets stressful, and I know no one wants to be doing it this way. And I know a lot of you are disappointed with the grades you've got, and the whole idea that we don't have part marks because of the way these things are marked, and because they're marked by a computer, which is really strict. And so if what's going to happen is the same policy I use for midterms. The whole reason we have these marked assignments, I didn't want everyone to have. I hate them. I would just rather have you have all these marks in the final, but I don't want to do that because then you get stressed out about the final having all the marks, and you can't win. So the policy is, it always is in my classes, that if you do better on the final than on any of the other evaluations that I control, so in this case it's going to be the Mobius assignments, your final grade will replace that. If you do better on the assignment, it keeps the balance stays on that assignment. So your final grade, if you do better on the final exam than you do on any of the individual assignments, that individual assignment's grade gets slid into the final exam. And the reason I do that is this course is constantly building on itself. And sometimes through no fault of your own, you're trying, it just doesn't make sense, it doesn't make sense. We come back to that concept a little bit later in the course when we're seeing it applied into something, and suddenly it all makes sense. And my goal is that you learn the material by the end of the course. If you haven't learned the material, you don't completely understand resonance at this point, you should get on that. But that's also not your fault. It is difficult, it is challenging, and what makes it go click for everybody is different. And so maybe they'll go click later. So if it's clicked by the final exam and you're doing well on that, then you shouldn't be penalized for having trouble earlier in the course. I'm going to send out a so the grade still stands, doesn't change the syllabus. It's just you get a better grade if you do better on the final. Okay, so we're going to actually, this is kind of like sort of a gentle pause lecture for a bit, because we're going to start really delving into mechanisms maybe later this lecture if I finish this PowerPoint, or very early next class. So we've sort of now set up all the requirements that we need. We've talked about stereochemistry, we've talked about charge stability. Now we're going to see them applied to reactivity. And I'm going to turn my video off because then the recording will have the slides bigger, which is good. Oops, mouse is on the wrong screen. Mouse is on the right screen. There we go. So this comes mostly from Chapter 8. If you need to, you might need to review Chapter 5. We're going to talk about alkenes. We're going to discuss the bonding. We've kind of done this ad nauseum, but we are going to discuss it again. Make sure we're all on page. A few notes on naming alkenes, though I know you guys have already been practicing, so that's good. We're going to move quickly. We're going to talk about the relative stability of alkenes. We're going to spend a little bit of time on that because it's very, very relevant. And then we're going to discuss how we can take these into account to predict relative boiling points and solubility. It's a thing. It exists. The MCAT loves asking questions like that. I don't care as much because they're all pretty much similar. Bigger size, higher boiling point. Surprise. So, alkenes are hydrocarbons with carbon-carbon double bonds. Fancy. So, they're also called olefins. And what I want to find here is a little bit of a difference. The alkene refers to the molecule as a whole. Olefin refers to the carbon-carbon double bond. So olefin is kind of like carbonyl. Carbonyl refers to a carbon-oxygen double bond. You can say carbon-oxygen double bond. That's a lot of words. Carbonyl is a lot shorter. And carbonyls are part of other functional groups. Just like an olefin is a carbon-carbon double bond. It can be part of another functional group, or it can be an isolated carbon-carbon double bond. And an alkene is the molecule as a whole. So 1-butene is an alkene. It has an olefin functionality between its first two carbons, or it has double bond between its first two carbons. So my lectures are actually derived from a course I gave to engineers, and so I keep talking about the industrial applications of these things, which I guess is still relevant to all of us. They're really, really important in plastics. Our entire society is basically, modern society is built on alkenes So we have basically polymerized the crap out of ethylene, and we spend a lot of time turning gasoline into ethylene, or really what Sarnia does for a living. And then we can turn into epoxides, and epoxides can be used to make polymers. We can also use it to make ethylene glycol, which is really, really good for antifreeze. We can make ethanol industrially under this process. It's not particularly good for drinking, but it's really good for adding to gasoline. We can make vinyl chloride. This is the basis for PVC. This is all your PVC tubing and CDs, and those of you who still buy CDs. I like CDs. And a lot of bottles. So a lot of commercial plastic bottles are made of PVC. You can take ethylene, you can convert it through, we're actually going to go over a lot of this chemistry. You can oxidize it to acetaldehyde and take it up to acetic acid. This is how we make commercial vinegar. We don't make commercial vinegar by fermenting grapes. That's too slow and grapes are expensive. We make it by taking oil out of the ground and oxidizing it. And then polyethylene is basically the building block of modern 20th century Canadian living, along with maple syrup, which is a sugar and not an alkene. So they're very important for polymerizations. Great. We are actually going to come back to all this polymerization chemistry at the end of the course because it uses free radicals, and free radicals are weird, and I don't really want that to be your initial introduction to mechanism. It's a very bad way to learn. It's very confusing. But these include things like Teflon. So for all those nonstick pans, which are no longer nonstick because you chipped off the Teflon, they originally were coated with these carbon-fluorine bonds, which don't stick to either water or grease, which is why they're nonstick, because they don't stick to anything, except other fluorinated things, but you shouldn't be eating fluorinated things. We make lots of this, 60 million tons per year in Canada, I think, alone. And Imperial Oil in Sarnia, these are actually pictures from Imperial Oil, is a big local employer, actually. And this is what they do. They make polyethylene from all the oil that they bring in. Also, tons of acetic acid is made from ethylene. Who cares? Details, stuff. It's important. Good. So bonding in alkenes, we've talked about this quite a lot. So if you just have a really simple alkene like ethene or ethylene, if you want to call it the old thing, but ethene is the IUPAC. You've got 2 carbons, 4 hydrogens. Everything is sp2, except the hydrogens, of course, which are s, because hydrogens are always s. It's what they do. And that means that you have a p orbital on each of your carbons. And I'm bored looking at this slide. The one thing I kind of like is this this space filling model down here, where the p orbitals, the electron density of the p orbital is kind of drawn almost like a lozenge or something. It's a little bit depressed in the middle and a little bit stickier on the side. So it's got that sort of drop in the middle, and that's an accurate shape for what the electron density looks like in a pi bond. And it's kind of discs on both the top and the bottom, but sort of elongated ellipsoids or things like that. I'm not good with geometry. What this means, though, is, of course, that these double bonds don't rotate. Again, this isn't news. We've been talking about this. You don't flip them, because if you flip them, you're breaking the pi bond, right? Because then the p orbitals are out of alignment as you're rotating, and that just doesn't happen. But you can take it from cis to trans, and we'll talk a little bit about that later, how we can flip cis to trans. And normally it goes that way because trans is normally more stable. So what is the bond energy of a double bond? Well, if you take the total bond energy in a carbon-carbon double bond, and you subtract the bond energy of your typical carbon-carbon single bond, you're left with the bond energy of the pi bond. And notice that it's less than the bond energy of the single bond. So the single bond is about 347 kilojoules per mole. Compare that to a hydrogen bond, which is about 5. It's 5 kcal, which is about 25 kilojoules per mole. But who cares? It's a lot smaller, is the point. And the pi bond is quite a bit weaker than the single bond, but not immensely weaker. Like 264 is a smaller number than 347. That is about as much detail as I want to look into the actual numbers of the bond strengths. When I was taught this course, I was taught this by memorizing tables of bond strengths, and I really hate numbers like this in chemistry. So relatively, it's about 3/4 the strength. A double bond is about 3/4 the strength of the single bond, give or take. Alkene nomenclature. Nomenclature is on your own, but this just goes with everything I'm talking about with the nomenclature, where you're perfectly fine to write this as 1-butene or but-1-ene. Both of those are perfectly acceptable. The 1 here will refer to the first functional group in the name. The first functional group is the En of the ene. So this is 1 of the ene. But if you want to be completely unambiguous and you find that confusing and you get lost easily, it's always fine to break up the name like this. So nomenclature of cis-trans. There's cis, there's trans. We're not really going to use that. We're going to use E and Z as we've discussed. So there are 2 ways you can have no cis-trans. You can have a situation where the groups are identical on one of the carbons. So this carbon here has 2 methyl groups on it. They have the same weight. They're absolutely identical. So this guy only has 1 isomer. It doesn't have an E and a Z. It only has 1 isomer because you can't differentiate between the 2 things on one side. And over here we have the same thing where we have 2 hydrogens. And then the whole cis-trans thing fails miserably when we get something. Wow, this is actually the exact example I used this morning. That was completely by chance. When it's ambiguous, and this is where we use the EZ, because it's not clear how we can, how we can call these cis and trans. The bromine is cis to the methyl group, but the chlorine is trans to the methyl group. So is this a cis or a trans double bond? And the answer is it's neither, because you can talk about the bromine being cis to the methyl group, but that doesn't say the double bond is cis. That you're talking about the relative positioning of 2 of the moieties. And that's where we use the EZ system. Again, we've gone over this, so I'm not going to go over it again, but just the list of ways to do it. Yes, separate the double bond into 2 ends. So we got something like that. So there's our 2 ends. Then we use the R and S rules to assign first and second priorities. Bromine, then chlorine, because bromine has got a bigger number. It's all about size. And so we've got the same thing on the other side. Carbon is bigger than hydrogen. Then if the first 2 priority groups are on the same side as Z, I'm going to remove that because that's offensive. I think it should be a German accent. So on the same side, there's Z. And if they're on opposite sides, they're on the opposite sides. And if I say that, that's like saying opposite in a Luxembourgish accent. No one can gainsay me because you've probably never heard a Luxembourgish accent. I have no idea what that is either. So in this case, the 2 big groups are on the same side. So this is a Z double bond. So if we have an example like this, we identify that we have 2 double bonds of interest. On double bond number 1, that is the priority over the hydrogen. The chlorine is the priority over this methyl group because chlorine is heavier than carbon. We don't get to the rest of the chain. We break the tie right there. So even though this is a bigger chain, much bigger than just a chlorine, it's the RS rules. Heavy atom first. Okay, same side on this one. This guy, hydrogens are across from each other. This one's pretty easy. That's 1, that's 1. They're on opposite sides. They're E. So we have a Z and an E. If we're going to number this if we're going to name this compound, because it'd be a shame not to at this point, we had to figure out what the root name of this molecule. So anyways, yeah, I'm just going to leave the Z and the E in there. We had to figure out what the root name of this molecule is going to be. I'm looking for oxygen. I don't see any oxygen. I look for nitrogen. I don't see any nitrogen. I'm stuck with double. I look for double bonds. That's the next most important thing. I see some double bonds. Okay, double bonds, most important thing on this molecule. Great. Now we need to figure out how to get those double bond numbers as low as possible because they're the most important thing. If I start counting from this end, the first double bond will be at 3. If I start counting from this end, the first double bond will be at 2. 2 is a lower number than 3. So 2, 3, 4, 5. So I've got a 2Z, 3E, so it goes in brackets. 5E, 5E, 5E. Alert. Cool. That takes care of my double bonds. There's no stereocenters on this. Well, there is actually, but it doesn't tell us what the stereocenter is. That's either an R or an S, but I have no idea which one. It's got 4 things attached to it. So we ignore that stereocenter. We're going to put a hyphen because those are numbers. We've got, or letters, we've got a chlorine on carbon 3, and we've got a chlorine on carbon 1, 2, 3, 4, 5, 6, 7, carbon 7. So it's a 2,7 dichloro. One, two, three. No, it's not 2. It's 3, 7. This is why I like writing these things out, all of them, before I start trying to write the name down. What else did I screw up? Nothing yet. That's good. And it's got 8 total carbons. And so what I could do is I could write a 2, 5 octene. Octadiene, sorry. Octadiene. I could also write octa 2,5-diene. That would also be completely appropriate. Where did you separate the double bond to get E and Z? So this one, this double bond here is Z. That double bond is E. This one's Z because the methyl group and the chloride are the heavy ones, and they are on the same side of the double bond. This one is E because the carbon and the carbon are the heavy ones, and they are on the opposite side of the double bond. And so double bond at carbon number 2 is Z. Double bond at carbon number 5 is E. So if there were chirality center, so if there was a stereocenter, so let's say we define that stereocenter. 1, 2, 3. Hydrogen is number 4. Hydrogen is backing away from me because I drew it like that because I'm lazy. And I can make up the question because that is the power vested in me. That's an S. That is on carbon 7. I just stick it out front there. No, you have to put the Z, E, and S's and all that stuff up front. I don't know why. Your way makes sense. That's probably why we don't do it. So we put it up there. It does, and I don't care. So I will accept any order of the Z, E, and S and R's. The normal thing is you write chirality first, and then you write double bonds afterwards. And no, I have no idea why. What about chlorine on the E side? Yeah, but the chlorine is not directly attached to the carbon. The chlorine is attached to the carbon attached to the chlorine. We're talking about this one, right? Mobius will care for order, which is why I'm going to be careful about how I ask these kind of questions in Mobius. Yeah, no, there was no way from what they had drawn to figure out the chirality. It was impossible. There was no chirality. They were drawing a racemate. They were basically saying it's a mixture, and so you don't need to supply it if there are no wedges. Okay, I'm going to move on because this is. I'm moving on because I'm bored. This is boring to me. Okay. Oh, I got numbers that appear. And the numbers agree with me. And my name is right too. Man, I really thought this thing through. Go figure. Okay. So stability of alkenes. We can measure the stability of the alkenes kind of the same way we looked at stability of ring systems. You burn them and you see how much energy is released. It's pretty crude. So if you take a monosubstituted alkene, like butene, so notice that we have the same molecular weight for trans 2-butene and 1-butene because it's the same number of molecules. And we're going to hydrogenate them instead of burn them. So we're adding, I guess this is not quite the same thing. So we're adding hydrogen across the double bond. We're going to come back to what that's like. And we can measure the energy released. And what we can see is we release more energy on the monosubstituted than we release on a disubstituted. So what this means is this guy was higher in energy than this guy. And it's because the two starting materials are identical, or the products are identical. The difference, like the thing you're subtracting, the product is the same. So the difference must be in the initial energy of the starting materials when you get these energies. So more heat released means it's a less stable alkene. So again, there was more energy released by the mono than the di, than the trans. The mono was less stable because it was higher in energy because it had more energy to release because they all go to the same place. And that's not negligible. That's a meaningful value. So what we actually see is a trend in alkenes. The more substitute the alkene is, the more stable it is. And this comes down to an idea of hyperconjugation. We're going to get to that in just a second. And trans alkenes are more stable than cis because electron clouds don't like being next to each other. This is the same thing we've seen with eclipsed. You don't want to be eclipsed when you're doing your butane cycling things through circles and stuff. And it's just like the cis guys, they're kind of stuck together because they're on the same side of the double bond and they're going to repel each other. And so cis is bad. Trans is good. So we see that the most substituted double bonds, the tetrasubstituted guys with 4 things on them, is the most stable double bond. We get less stable with tri-substituted. Then the trans is the next best, like the next most stable. And again, it's because the two big groups are apart from each other. The geminal is the next most stable. And this is a little bit surprising because when you draw it, you're thinking, well, those actually look really close together. Like those look closer together than that. But they're not. Surprise. So that's because they can rotate out of the plane a bit better. And so the geminal is more stable than the cis. So you kind of got this. Everything else is easy because there's only one way to get 4 of them on there. There's only one way to get 3 of them on there. There's only one way to get 1 of them on there because it doesn't matter where the other ones are. Everything else is a hydrogen. There are 3 ways to get 2 groups on there. Trans is the best, then geminal, then cis. This slide is, I guess, kind of important. And I'm actually going to run through this and we're going to come back to hyperconjugation. So stability of cyclic alkenes, unsurprisingly, think about the geometry. We already talked about stability of alkenes, and we said sp3 carbons like being 109.5. sp2 carbons like being 120. But it doesn't matter if it's an sp3 or an sp2. If it's in a triangle, it's 60 because that's what triangles are. So that is a really unhappy double bond because it wants to be 120 and you're forcing it to 60. It's much more unhappy than if it was a single bond, which wanted to be 109 and you're forcing it to 60. In general, 5-membered alkenes are pretty happy, but 3 and 4 are not happy. They want to react. Cis versus trans cycloalkenes. So if you start trying to draw a chair or sort of a six-membered ring, that's a cis-double bond. That looks okay. But if I ask you to draw a six-membered ring with a trans-double bond, well, there's 4 of my atoms, and this guy you just can't reach. Like you just can't reach, right? You've only got 2 more atoms, and it's like, okay, well, that is a really unhappy system. It actually doesn't exist. If you get out your model kit and try and make a trans double bond in a 6-membered ring, and you will break your model kit because it won't want to do it. The heptene, the 7-membered ring, it becomes possible if you really squish your model kit together. Like, your model kit tells you what angles it wants to make, and it's kind of like reality. And an 8-membered ring, you're okay. You're good on an 8-membered ring. You can make trans, but cis is still more stable. And so this is one of those cases where cis is more stable than trans, and it's because of ring strain. Because the trans induces this torsional ring strain into the molecule, which is separate from the steric strain that's caused. So you need a big enough ring. I think at about 12 carbons, then the trans becomes more stable than the cis because transes are more stable than cis normally. But it need to go up to about 12 members of the ring to make that feasible. Does this matter? No, not really. Don't draw any 6-membered rings with a trans double bond. I will freak out. Okay, there is a rule. It is called Brett's rule. It shows up on NCATs. It is very important when you start doing a lot more chemistry. For the purpose of this course, it is not an important rule. And so it just has a lot of jargon in it. A bridge bicyclic compound cannot have a double bond at a bridgehead position unless one of the rings has at least 8 carbon atoms. What the hell does that mean? What it means is if you have a molecule like this, I don't know where my mouse is. Where's my mouse? There. It should be on this screen. It's not on this screen. What's it doing? I don't understand. Okay. So what we've got with this guy is this is bridged. There is a bicycle, there is one cycle, and there's a 6-membered ring. Notice it's also what this is forcing this double bond to do is be tri-substituted, so it's actually kind of trans here. It looks okay, but that's a trans double bond in a 6-membered ring. That is bad. That's really bad. It's also just way too strained. Now we get up to an 8-membered ring, we're allowed having trans double bonds in those. And so we can have a trans double bond at this bridgehead connected to where the 2 rings come together, where there's 3 carbons attached. Again, this rule exists. I don't think I've ever evaluated on it, and I'm not going to start. So alkene physical properties. Things depend on the same things that they do with alkanes. Maximize surface area, good. Maximizing surface area gives you higher boiling points. And that means molecular weight and branching. So how many carbons you have, more carbons you got, the more surface area you got, makes sense. And branching, the more branching you have, the tighter your structure, so the less surface area you've got. So that makes sense. Polarity of these guys does depend on if you have Z or E double bonds, and because unlike in an alkane where you have free rotation around that bond, these guys are locked. So if you have this dichloroethene, cis dichloroethene, the 2 chlorides are pulling in the same direction. You have a net. My cursor's not over there. I don't know why my cursor suddenly disappeared. But you have a net dipole going straight up. So this molecule has a net dipole. That means you have access to dipole-dipole interactions, which means the interactions between molecules are going to be stronger than you would expect. Yeah, I guess it just... Oh, I have no idea what's happening anymore. Okay. Whereas with the trans guy, they're pulling up equal and opposite each other. They cancel each other out. There's no net dipole. You get a lower boiling point. Surprise. So, alkenes, molecules with double bonds, important for chemistry. Ez is important. You're going to need to know that. So more substituted alkenes are more stable, and that's because of hyperconjugation. And we're going to get to what that whole hyperconjugation thing is, because it's going to be really important for our next lecture. And the physical properties are similar to alkanes, but you don't have the free rotation that alkanes have, and so you lock into configuration, and so you do get net dipoles. That's going to be the end of that slideshow. I'm going to add more slides to it because I want to talk about hyperconjugation. So I'm just going to add a bunch more slides. New slide, new slide, new slide. Okay. Sorry, I lied when I said it was the end of the slideshow. It is a continuation of the slideshow. So this is hyperconjugation. So we've talked a lot about charge stability, and this is like the last thing we haven't discussed. No, second last thing we haven't discussed. So we'll get to the last thing today too. Might as well finish off everything you need to know about charge stability. So let's think about I'm going to draw line arrow angle formulas. I'm going to draw line angle formulas. Let's think about these three molecules and this poor stupid molecule over here. These are all cations. I've lost my chat window. I'm going to bring my chat window back. Shoot. Oh, there it is. So we have these three guys, and what I'm going to tell you right now is we can classify these. These are all carbocations, not cations. They're not from Mexico. Carbocations. This is called a tertiary carbocation because it is a carbon with a cation attached to three other carbons. And I've got a cat here. You want to participate? No, she wants to lick herself. Okay. This is a secondary carbocation. This is a primary carbocation. And again, it is because it is a carbon attached to a single carbon. And this is a methyl carbocation, or sort of a zeroth order, because that carbon isn't attached to any other carbons. Great. Who cares? So in general, more stable, less stable. Tertiary is far more stable than secondary, is more stable than primary, is far more stable than methyl. Methyls basically do not exist. I'd argue that under normal circumstances, primary carbocations don't exist. Somebody managed to actually see one, but they tried really, really hard. Like really, really hard. And it was kind of a little crazy. So tertiary and secondaries exist. Primaries can exist if they're properly stabilized by resonance. Cool. But everything we know about how charges are stabilized, none of that explains any of this right now. So what we're looking at here is an effect called hyperconjugation. So let's think about what these actually look like. I'm going to turn my video on because I think I'm gesturing more right now. So with this, what we have is we have a central carbon that has an empty p orbital. That empty p orbital is the carbocation. It is an empty orbital. It is a p orbital. If you take a look what these carbons are doing, they've got their 4 orbital for their valence shell. They are missing an electron because I just told you that because they're carbocations. So they got 3 electrons. I mean, well, how best can I organize that? Well, I'm going to take those 3. I'm going to mix them together in my blender. And I'm going to pop out 3 sp2s and an empty p orbital. And this is great because I can get those electrons down to sp2, which is pretty low, lower than sp3, and I get to leave a p orbital empty. So I kind of get this. The p orbital is much higher in energy. It would cost me a lot of energy to have an electron in there, but I don't have any electrons in there, so whoop-dee-dee, I can leave it empty. And that's why carbocations always become sp2. I'm trying to think if they ever become sp. They probably do, but I can't think of any off the top of my head. This has explained absolutely fuck all at this point. So what I want you to think about is what's happening on the adjacent carbons. Well, I've just drawn CHs. They're just all methyl groups. They're very boring. So let's just draw that. So these are sp2 bonds. Just because of crowding, I'm going to draw this guy on the bottom, but I'm going to shade them in. They're both shaded because they have to be. But if I shade the hydrogen, I'm going to write the hydrogen next to it so I can make sense of that. I don't know what these hydrogens are doing. I'm not good at drawing in 3D. They're there. They're off the plane. It's complicated to draw them. Okay, so we have that. Now again, this is an empty orbital. And nature abhors charges, does not like full charges. So if you're looking around and thinking, how can I help make this carbon's burden a little less? Well, I've got 2 electrons in this CH bond. Now, if I just, conveniently covered up the hydrogen temporarily, that looks an awful lot like half a lobe of a p orbital. And it's now lined up perfectly with another p orbital. So, that looks like you can make a bond there. Right? You got these electrons. They're right next to an empty orbital. There's 2 of them. That looks pretty good. Now, you can't quite do that because there is this pesky little hydrogen on there, and it is there. But these electrons can donate into that empty orbital and make it a little less positive and move a little bit of that positive charge over onto this adjacent carbon. These electrons over in this guy can do the same. These guys over here, can't draw them in the orbital because it's shaded, can do the same. So you have 3 of these effects with sp3 orbitals on the adjacent carbons. It can be sp2 orbitals, it doesn't matter, are able to line themselves up to be parallel to that p orbital, and they can donate their electrons into that empty p orbital. And suddenly, I'm less positive. And that's a good thing. Now, let's just jump directly to the primary guy, because I'm sure you're smart people, so you can do things by analogy. So if we think about the primary guy, primary carbocation that we have up there, suddenly, well, this doesn't look so good because, yeah, I got 2 electrons here they can share in, but I've got hydrogens on these spots, and they can't because they don't have an sp2 orbital, so they can't help. I'm still pretty positive. And then if we jump to the methyl guy, well, he's very lonely. He's completely positive because there are no hyperconjugation effects available to him. So what's this whole hyperconjugation thing? Well, conjugation is resonance, right? P orbitals interacting with p orbitals. This is kind of like resonance, but not. So it probably should be called like hypoconjugation because it's not as good as conjugation, but I guess the person who named it didn't know their Greek, and so they called it hyperconjugation, which to me means kind of like superconjugation, but it's kind of like less than conjugation, so I don't know why it's superconjugation. So like everything else in organic chemistry, it doesn't make any sense. And so I think that's what we're looking at here is the conjugation is resonance. The hypermeans is kind of like conjugation, but not completely. And it's resonance like interactions that are occurring with sp2 orbitals or sp3 orbitals interacting with the empty p orbital. And what you're doing is you're decreasing the overall positive charge on that central carbon. And that is a good thing. That is what hyperconjugation is. Now, along with, so what I'm going to say is I'm going to say hyperconjugation a lot. And the hyperconjugation effect is two things. One is this thing I just showed you. The second thing is you do, of course, have inductive effects. And inductive effects don't happen between these orbitals here. The inductive effects are happening through the single bonds. So in a tertiary, we can pull some electron density in from all three carbons. This is separate from the hyperconjugation. This is an inductive effect. In a secondary, we only got two of them. In a primary, we've only got one of them. In a methyl, we don't got any of them. We're already pulling from the hydrogens, and you can't pull as much from a hydrogen as a carbon. So there's two reasons why the tertiary carbocation is more stable than the secondary. One is hyperconjugation. The second one is this inductive effect. They always parallel one another. I'm going to just refer to them collectively as hyperconjugation, but there's kind of sort of two independent things that are contributing. But they both, when one is better, the other one's always better as well. I'm going to pause for a second and see if anyone's got any questions, except can you explain the whole thing again, because I didn't understand any of that. Which would be fair. Thank you, Janik. So I would define hyperconjugation as interactions donation of electron density from collinear, i.e. parallel, sp2 or sp3 orbitals on adjacent atoms to an empty p orbital, which is a positive charge. Yes, the CH needs to be aligned with the empty p orbital. And it doesn't need to be CH. It can be CC, it can be CO, it can be C anything. It just needs to be an sp2 orbital. It can be an OC. Like you can have an oxygen there doing hyperconjugation. You just need to have an sp2 orbital. So hydrogen can't do it. Everything else can do it. So what we're really looking at is how many things that carbon attached to that aren't hydrogen. It's just what we're going to find out is that when we have a carbocation and the atom next to it is not carbon, it's like oxygen or nitrogen, then resonance becomes like normal conjugation becomes more important because you got a lone pair and it can be in a p orbital and then you got full resonance. So the hyperconjugation is kind of like a pathetic weak form of resonance for things that can't do resonance well. Yeah, sharing is caring. That's exactly it. Electrons like spreading, right? We want molecules are all in it for the entire molecule. And they don't want any one of their atoms carrying all the charge because charges are heavy. So they want to spread negative charges around. They want to spread positive charges around. That's why we see induction. That's why we see resonance. If nature, for whatever reason, wanted to, like, was different and we wanted to isolate charge in one place and that was the way to do it, then we wouldn't have any of these effects. But nature wants to minimize charge. It wants to spread charge around as much as possible. Yeah, this guy's primary. I didn't draw a secondary. Mostly because I don't like drawing the hydrogens over here with these stupid angles, and it makes me nervous, and I don't have to if I draw the primary. If it was a carboanion, it is actually the other way around. So Babian asked if it was a carboanion, everything would be the other way around. Yeah, because that negative charge is looking for it. It wants to share into empty orbitals, or it wants space, and an sp2 orbital is full, so a negative charge can't donate into an sp2 orbital. So it wants negative charges want to be primary. So I've just drawn this with all the positive charges. Tertiary better than secondary, better than primary, better than methyl. So we see the opposite effect with negative charges, which is, gratifying because something makes sense. And again, it's induction works the wrong. Induction counts against you here because the carbons are kind of electron donating, so it's not good to be there. And you have the kind of opposite hyperconjugation thing where now you have these electrons, there's nowhere to put them because everyone else has got all their electrons and those orbitals are full, and it's awkward. It's not completely true, but we'll come back to, and we'll sort of come back to that later. Can I explain why what? So the last thing I want to discuss with this, with negative charge is the opposite effect. Well, okay. So in a positive charge, we have this hyperconjugation thing. Electrons want to move towards the center because there are electrons in these adjacent orbitals. And the other thing we need to remember is, yeah, we want to minimize charges, but the other thing is that electrons hate other electrons, right? They're actually a lot like cats. You just can't have too many cats nearby because cats don't get along with other cats. Well, okay, maybe your cats do. And I got two of them, and they kind of get along with each other, but I don't know if I had like. I have a colleague who has a partner who wants a cat army, and I'm not sure if a cat army will get along with the entire army. It might be an awful lot of infighting in the cat army. So if you have a negative charge on this guy, let's say a carbanion can be either in a p orbital or in an sp3 orbital. Normally it's in an sp3 orbital because that's lower in energy. So let's just take a look at this. So first of all, the first thing that jumps to you is like, shit, it's in an sp3 orbital. I'm just going to draw a primary. So now suddenly alignment's not possible. Like, you can't get the orbitals all lined up to kind of donate in. And even if you could, think about what you're doing. Like, let's just say these were all hydrogens. And they're all the same, right? But let's say these electrons are trying to interact with this orbital. Well, that guy's got all of his electrons. Why does he want more electrons? And now you have electrons near electrons, and electrons, electrons. Everywhere there are electrons, and they want to all get away from each other, and they can't go on vacation, and so they're stuck too close. And so you want to minimize the number of electrons near your other electrons. And you minimize that by having the methyl. Because then you have all this space, and all you got is some hydrogens, and nothing's in the way, and it's very calm. I never know what's going to make sense. So hopefully you're not just giving me a pity thank you, and hopefully that helped. So the last thing I want to discuss is charge based on, negative methyls exist. Methyl lithium is a good example. We'll use it later in a bunch of lectures. It sets fire to everything. So it's a lot of fun. The last thing I want to talk about was relative charge stability based on hybridization. I've just I just spent a few seconds there trying to find a word and was drawing things instead and talking about setting fire to things while I was trying to figure out what I wanted to say. Now let's stick with the trend of having carbons. I guess that's right. One on the bottom is the least stable, and one on the top is the most stable. The only difference between these, okay, there's a few differences, right? But the main difference between these guys and what matters is the hybridization state of the atom that this is on and what orbital this is in. This is in an sp orbital. This is in an sp2 orbital. This is in an sp3 orbital. It could be in a p orbital if it could be involved in resonance, but there's no resonance here, so it's going to be sp3. And there's no in none of these cases can a negative charge be involved in resonance, because the molecule next to it doesn't have a free orbital available to interact with it. Okay, so why is sp more stable than sp3? I don't know if anyone wants to throw a guess out there. Yeah, that's actually completely the right answer, Emmanuel. SP character. So what? There we go. Okay, the first two answers are both correct. Yeah, you're closer to the nucleus. You got less P character, you got more S character. And remember, S is a circle, P is like a loopy donut-y, I don't know, like a barbell kind of balloon animal thing. P, the average distance from a nucleus, is bigger than in an s orbital. So in an s orbital, the electrons are closer to the nucleus. So that means your electrons are closer to your positive charge. So that means you decrease charge separation. Electrons like being close to positive charges. So they're happier in sp orbital than sp3. No, sp is not more electronegative than sp3. Electronegativity is a function of the atom, and I don't like that. I would say that an sp orbital better stabilizes a negative charge than an sp3 orbital. We misuse the term electronegativity a lot. Like, if you remember what it actually means, it's defined, that number is defined as the amount of energy you need to add an extra electron to the molecule in the gas phase at infinite distance from every other atom of the same type. And we use that as a proxy for how much this thing likes sucking electrons from other atoms. It kind of works, but we need to remember where that number comes from. And so I'm very, very nervous about talking about anything except the atom's electronegativity and how it's not that electronegativity tells you how well a bond is going to be polarized. It's just that the way that atoms pull electrons from other atoms in shared bonds parallels electronegativity, unless size comes into account. So it's kind of like electronegativity and the way this thing are pulling atoms are both symptoms of the same common disease, which is, the atom's ability to pull more electrons towards it. But that's not the same thing as electronegativity. They're very similar. They both kind of arise the same thing. They both kind of trend together, but they're not the same thing. Cool. So these two features, if we're going back, damn it, I misjudged how many screens I needed. I needed one more. Oh, wow, I've gone way over. I'll finish this next class. I've gone like 6 minutes over. I try not to do that. I'm sorry. Those of you guys who need to run off to lab, please run off to lab. And I'll upload all this stuff. And we'll be talking more about this in a lot of detail starting next class when we're starting to work on mechanism.